Hi, my name is Pone with the Fuck Barbecue, and today I wanted to discuss some simple linear regression. So what the fuck is simple linear regression? So simple linear regression is basically a statistical model that determines the relationship between two different variables, and it follows this general format of y equals mx plus b. Simple linear regression differs from this thing called multivariate linear regression because in simple, there's only one x value, but in multivariate, also known as multiple variables, there are multiple different x values to determine the single y value. And so x and y values are also known by different names. X is also known as your independent, your explanatory predictor, and y is also known as the dependent response and outcome. So since this discussion is focusing on simple linear regression, allow me to break the actual equation down. So y equals mx plus b is the equation of a line. So y, as previously stated, is your dependent variable. X, as stated earlier, also is your independent variable. So when these new variables that are introduced are m plus your b. So m is your rate of change or your slope of the line itself, slope / rate of change. And your b value is another term for your y-intercept. So I guess I should use this as an example because examples are often sometimes teach the most. Moving that. So I guess here in a perfect world, I decided to write this type of example. Let's say we're tracking the number of apes that have joined Super Stonk. All right, community since it first began. For the moment, we live in a perfect world. The number of apes. So the number of apes also is going to be our y variable, has increased by 1,000 with each passing day. So then our day is going to be our x value, whatever. So basically, since it's increasing by 1,000 apes per day, this is saying that the rate of change, also known as the slope, is going to be 1,000 apes per 1 day. To make a diagram of this, or a table, so from that example, we have day 0, which was going to be, there's 2,000 apes. So right off the bat, we have 2,000. Day 0, boom, like 2,000. So then because we're increasing 1,000 apes per day, we're going to take 1, and then that's going to be 3,000, and then 2, that's going to be 4,000, and blah, blah, blah. I'm going to all the way to 10 because it's a good number. It's going to be 12,000. So we can take this simple table and plot it. We can have our x and y values. So 1, 2, 3, 4, 5, 6, 7, whatever, up to 10. So we can place our x values, which is our number of days, 5, 6, 7, 8, or whatever. And we can make these values. So we'll just basically plot these values here. So at day 0, there's 2,000 here. Day 1, 1,000, 2,000, 3,000, whatever. So it makes this line right here. And so with all this information here, this effectively gives us the overall equation of the number of apes is equal to 1,000 times the day plus 2,000. This is our resulting equation because our rate of change is 1,000 apes per 1 day. Our y-intercept is over here at 2,000. And everything's pretty solid. It's a very lovely, perfect world linear regression line. But you know, the world sucks balls. So, you know, that's never gonna fucking happen. Because we don't live in a perfect math example. So fuck. So let's move on to a type of example that would be more realistic in its count. And so I decided to make a table. So we have our days again, then we have our number of apes. And from here, instead of having exactly 2,000, we're gonna have on day 0, there's 1, day 2, or day 1, there's 2,999, day 2 is 2,876, 3, 5, 2, 8, 5, 4 is 7,215, 5 is 7, 8, 8, 7, 6 is 8, 80, 20, 7 is 9, 6, 4, 2, 8 is 10, 5, 7, 9, 9 is 1, 1, 35, 7, and then our 10 value is 12,857. So data like this is way more believable because we don't live in a fucking perfect world, so it's going to be all over the place. So if we were to graph this, the days versus ape, the number of apes, so this would be our day value, and this would be our ape value. Instead of having this perfect line of where all the dates values are, it would have dots. The actual values would be more or less above or below this regression line. So I already previously calculated using this data the corresponding regression line for this. So using this data here, the overall line is equal to 1088.2 x plus 1945.6. And also I want to introduce some value called the R squared. So the R squared for here is 0.9872. All right, so what the fuck is the R squared? So the R squared is a value within stats that ranges from 0 to 1. And basically it determines how good our model is at being able to model. It basically said how good is our model. So if the R squared is equal to 0, it's a piece of shit. If R squared equals 1, it's pretty fucking solid. So that's how they differ. So majority of, depending on how you apply your R squared or your regression model, some statisticians use 0.8 and above. I do R&D in the real world, so my R squared is like, I'm okay with anything above like 0.65 and above. But general rule of thumb for type of stats is 0.8 and above, and your model is pretty solid. Anyways, so what does this mean here? So for this table that we made for our regression line here, which is equal to this line right here, and we have an R squared of 0.9872. Because 0.9872 is very close to 1, this regression line is fucking great at being able to determine the number of apes that's going to like be there on any given day. But let's introduce things called the error though. So what is error? So the error of this shit basically is going to be your actual value minus the theoretical. So let's say that this is day 10 and that's going to be 12,857, but from previous examples or the theoretical, it was supposed to be about 12,000. So we have an error of 8,057. So incorporating this error into the general linear regression, the actual final equation of the line is y equals mx plus b plus your error. So that basically is simple linear regression in a very quick time frame. So y(mx) plus b plus your error. And that's awesome. Cheers.